around us. All around us, water, moisture, the medium of life itself. Water with dissolved gases, dissolved salts. Water sustains. Water corrodes.
There's no doubt about it. Corrosion costs money. More, really, than most people would imagine. In the planning stages of a major development, substantial funds are earmarked for the use of corrosion-resistant materials. If corrosion-resistant materials are not used, a continuous maintenance program is needed throughout the life of the project. Corrosion is a fact of life. There are many ways of controlling it. All of them cost money, but it's an investment that is well worthwhile.
We can't control corrosion until we know what it is.
Corrosion is the inevitable return of a metal to the oxidized state it was in when it was native to the earth.
This is iron ore, the raw material for steel. Industrialized countries use a lot of steel. North America consumes nearly half a ton per person per year. Energy changes the ore into metal. Metals react with oxygen and water to release the energy and to change the metal to corrosion products. On iron and steel, it's called rust.
It takes a great deal of energy to transform ore into metal, but this energy wants to be released, and it will be released sooner or later in the corrosion process. Some metals have more energy to release than others. That is, some metals have higher oxidation potentials than others. Luigi Galvani discovered this accidentally when he put a copper hook through the torso of a frog and hung the hook on an iron railing. The wind blew and one leg touched the iron. Current flowed through the frog's legs, causing them to twitch. Galvani had discovered a primitive battery, and the legs of the frog acted like a meter.
In this galvanic cell, the copper strip is out and represents the copper hook. The iron strip is the anode and represents the railing. The meter serves the same function as the frog's legs. It indicates an electric current.
There's something else happening here. If the two metals are left in the solution for a period of time, the iron will rust. The copper will show no sign of corrosion. Iron is more active than copper.
What we are seeing now is the galvanic series. Each metal named is more active than the metal beneath it.
When any two of the metals in the galvanic series are connected in an electrolyte, a galvanic cell is created. If the potential difference between the two is great enough, the more active metal will protect the less active metal from corrosion. This is called cathodic protection.
And in fact, aluminium, magnesium, and zinc are used commercially as galvanic anodes to protect steel.
When the galvanic anode and steel are connected in a corrosive environment, the anode will sacrifice itself to the steel, and the life of the steel is extended.
With this knowledge and no more, we can extend the life of most buried and submerged steel structures.
Normandy, the coast of France, where steel from the fortifications of World War II lies rusting. Where Mulberry Harbor has crumbled from the corrosive action of the sea.
All corrosion is a form of electrochemical reaction, even within a single piece of metal of what looks like the same composition. Tiny differences in potential exist from place to place, and this results in the formation of local cells with distinct anodes and cathodes. I can stop the local cell action by applying a sacrificial anode that is more active than the local cell anodic potential. If I join a zinc anode to this piece of steel, the steel cannot corrode even in seawater until the zinc itself is consumed.
This is the 18,544-ton container ship San Juan. And like all steel-hull ships, it's like a huge galvanic cell, a floating battery.
The ship has a steel hull and a bronze screw. In this situation, the steel becomes the anode and the bronze becomes the cathode, and the seawater the electrolytic solution. The steel, therefore, tends to sacrifice itself to the bronze.
In dry dock, huge zinc anodes are welded to the vessel's hull. The zinc protects the steel, and if it is replaced from time to time, it will continue to protect the steel.
There are other ways of stopping corrosion. Remove oxygen and water from the steel surface. Then it will never corrode.
We could place the metal in an envelope to separate it from moisture and the dissolved gases that cause corrosion. Paint can provide this envelope.
But if the paint should be scratched or damaged, the exposed metal will rust through local cell action. The rust will then force the paint film, for that is all it is, away from the adjacent surface.
The situation requires maintenance. Removal of the formed rust, and then more paint, followed by the need to paint again, and again, and again.
Of the three anodic materials, aluminium, magnesium, and zinc, only zinc gives cathodic protection when incorporated into a coating. Zinc dust, mixed into specially formulated resins, yields a type of paint called zinc-rich paint. Even if the surface of the paint is broken by a scratch or some other abrasion, the zinc will sacrifice itself to save the underlying steel from corrosion. So we have produced a paint capable of giving cathodic protection.
Here in the test lab, we're comparing zinc-rich paint with normal paint in artificial seawater. You can see the effect of cathodic protection on the unpainted area of the test panel.
Metal spray is another commercially available method of applying the cathodic protection of zinc. The zinc is melted and sprayed at high temperatures onto the surface of the steel, where it solidifies to form a continuous coating.
But by far the most important zinc coating method is galvanizing. Prefabricated steel articles are dipped into a bath of molten zinc to form a continuous metallic coating.
In the galvanizing process, the iron and molten zinc react to form iron-zinc alloys. This creates a metallurgical bond between the coating and the underlying steel. It is this bond that assures good adhesion. The alloys form distinct layers visible under the microscope.
Steel strip is galvanized continuously in coils.
The continuous galvanizing process yields a uniform coating with a closely controlled alloy layer. The finished sheet can be bent and stretched without causing the zinc coating to crack or break.
Wire and pipe are also galvanized by the hot dip process.
Very thin but attractive zinc coatings for non-critical uses can be applied by electroplating.
The dull gray coating of the Sheridizing process is achieved by a dusting and heating method. Once again, the steel is protected.
How much lower depends on the location and the type of atmosphere.
In Pittsburgh, Pennsylvania, after 2 years, the corrosion rate of steel was about 13 times higher than zinc. In London, England, 17 to 21 times. Ottawa, Canada, 19 times. In Melbourne, Australia, 37 times. And in Daytona Beach, Florida, the corrosion rate of steel was more than 160 times that of zinc.
We also know that a zinc coating 50 micrometers thick lasts twice as long as a coating 25 micrometers thick.
So, from the known corrosion rates and the coating thickness, we can now predict how long a zinc coating will last. We can plan a maintenance program to obtain the maximum economic benefit from the investment in the zinc coating.
This economic decision has been made over and over again. A predictable life, a predictable level of protection, an appreciation that the effects of corrosion can be controlled, that maintenance and replacement can be planned. It is a matter of choice, not chance.
You can extend the protective life of the zinc coating and provide a colorful finish as well. We apply the best quality paints to galvanized steel.
The paint adheres to the zinc as tightly as the zinc bonds to the steel for maximum formability.
The combined effect of galvanizing and painting is more than you'd expect. The paint actually extends the life of the zinc, and the zinc assures the maximum life possible for the paint.
Over galvanized steel, this paint looks good after 10 years, and it will probably still look good after 15 or more.
They call it a synergistic effect. The combined effect of galvanizing and painting is greater than the sum of both effects taken separately.
Structural steel can benefit from this same synergistic effect through the use of paints specially formulated for galvanized surfaces.
In the humid atmosphere of the world's largest flower market, maintenance could be a nightmare because paint solvents would damage the flowers. The problem is solved with galvanized steel.
But is there enough zinc to do the job? Iron is one of the most plentiful of elements. Is there sufficient zinc to act in partnership?
You can find zinc nearly everywhere in the world. Abundance means reasonable cost.
The ore can be extracted from open pit mines or from deposits located hundreds of meters below the surface.
It is crushed and progressively ground until it is fine enough to be floated in a froth that permits separation of the sulfide ore from the waste rock. The sulfide concentrate is roasted to form calcine, from which zinc metal can be recovered by several methods. One of these is leaching in sulfuric acid and purifying to remove copper, lead, and other trace elements.
Zinc, more than 99% pure, is electroplated from the sulfate solution, melted, and cast into ingots that are stored and shipped to consumers. Protection with zinc. How can it be applied?
A Canadian winter. To reduce icing conditions for traffic, tons of salt and sand are spread on each mile of highway. The salt and melted snow seep through concrete and attack the reinforcing steel.
Local cell action occurs. The steel rusts. The pressure caused by the rusting process spoils the concrete and accelerates the decay of the metal.
Cars, subject to road damage, open to the elements, subject to changes in temperature, and plagued by rust.
The difficulty is that rusting starts from the inside and works out. Some people think that the answer lies in heavier gauge steel. They're wrong. In a world that is wet, subject to abrasion, and inaccessible for maintenance, how can the steel reinforcing the shafts be kept at maximum strength?
The marine environment is just as destructive to unprotected reinforcing steel. The corrosion cost is staggering. Steel in this environment would show signs of corrosion in days. Steel, galvanized rebar, encased in concrete, to stand in the North Sea for 30 years. Steel, to withstand an inhospitable environment for a predictable period of time.
Once the appreciation is generated, once the concept is accepted, proven again and again, then zinc-protected steel begins to appear everywhere. This transportation center is dominated by zinc in all the media of application. There is not a trace of rust, not a stain, not a break in the smooth surfaces of the metal.
In large items and in small, zinc plays its protective role. The logic behind its use is inescapable. Once that logic is accepted, zinc must be used.
The use of zinc is visible and it is invisible. Visible in 1,000 common applications. Invisible behind concrete, but it's there. There increasingly, because it works, and because it works economically. Cost?
This is where corrosion control starts, at the drafting table. It all costs money, either in the initial capital outlay or in maintenance later. A quick paint job in the beginning may look economical and easy, but it could end up being an endless headache. Of all the reasonable options, zinc-coated steel is worth thinking about.